Good afternoon, everyone. We are Aros team, and today we'll present our Capstone project, an AI-powered network traffic visualizer that detects anomalies using machine learning model. Here's the table of contents of our application of our presentation. First off is we will talk about the project overview, and we're gonna talk about the market research and literature review. And next we're gonna talk about the solution design, and finally our demonstration for our application. Let's start with the project overview. Cybersecurity threats are growing and smaller organizations are paying the price. In 2023, 40% of all cyber attacks target to small businesses, and shockingly, 60% of those businesses closed within 6 months of a breach. The average cost of a breach worldwide is now $4.5 million, a figure devastating for small and medium enterprises and schools. Educational institutions are also struggling. 60% of universities and schools were hit by ransomware, with the recovery cost averaging over $1 million. And now you might ask, don't security tools already exist? They do, but here's the problem. They are too expensive for SMEs and schools with limited budgets, and they are too complex with dashboards designed for cybersecurity professionals, not for everyday staff. So what's our solution? We are building an AI-powered network traffic visualizer designed specifically for under-resourced organization. We use our self-trained machine learning model trained on the CIC 2023 datasets to detect anomalies in the network traffic. Next up is the market research part.
So next is market research and literature review. On the market, there are existing tools that can monitor our network. We have open source tools like Wireshark, Snort, Suricata, and Zeek. They are free and powerful, but they come with major limitations. They require some technical skills to use and configure, and the interface can be overwhelming for non-technical staffs. On the other hand, companies like Palo Alto Networks, Fortinet, Cisco, and CrowdStrike offer very comprehensive solutions. They provide integrated protections across endpoints, and networks and the cloud. However, these solutions are expensive and complex to manage. So when we compare the two, there's a clear gap. What small and medium businesses and schools actually need is a solution that is affordable, lightweight, automated, and easy to use without requiring cybersecurity expertise. Next, let's look at how machine learning can impact anomaly detection. Traditional models like random forest, gradient boosting, and SVMs are widely used. They work well on structured datasets and are interpretable, but they can struggle with imbalanced data. Deep learning models such as CNNs, RNNs, LSTMs, and autoencoders achieve excellent accuracy and can capture complex traffic patterns. The drawback is that they require high-performance hardware, which makes them quite impractical for small-medium businesses. For resource-limited environments, lightweight methods like tree-based ensembles, especially random forests, strike the right balance. They are efficient, accurate, and interpretable, which are well suited for those with limited budgets and standard infrastructure. And our solution, NetSentinels, aim to bridge that gap and meet the requirement of the small-medium businesses. It is affordable since it's run on consumer hardware without expensive license. It is local first, so organizations don't have to depend on cloud service and can keep their data private. It is lightweight and automated using Scopy for real-time packet capture and a random forest pipeline for anomaly detections without manual rule update. And most importantly, it is usable. We provide a clear dashboards for non-technical users as well as structured logs like CSV and PCAP for technical staff. In short, NetSentinels brings together the strength of both enterprise and open source tools, but in a way that is practical and accessible for SMEs and schools.
The solution design consists of five main functions. The first one is packet capture. The backend uses Scapy to capture live network for analyzing, extracting the information needed to be displayed on the dashboard. The dashboard shows chart table to visualize data like bandwidth, protocol breakdown, and devices that connected to the network based on the result that backend send on real time so that user can always stay up to date with the network status. The app has ML models that can detect threat from the network flow. Any threat detected will have its information sent to the monitoring screen within 1 second and exported to a CSV and PICA file for further analysis. Here is the system architecture of NetSentinel. Starting on the right, we have the Internet, which provides the live network traffic. Incoming packets are first captured by SCAPI, our packet sniffing and feature extraction component. SCAPI breaks each packet into detailed flow information such as protocol type, header length, and traffic statistics, and then forward those features to the fast API backend. The backend has two main jobs. First, it coordinates with our AI prediction model, which uses a two-stage machine learning pipeline to classify traffic as normal or potential threat. Second, it serves this processed data and prediction result to the user interface through REST and WebSocket endpoint. Exporting thread data is done automatically from the backend. Next is the frontend, built with Next.js and Electron. This desktop application displays real-time network status, device list, and any detected anomaly on the app. The entire system runs locally on a single machine, which keeps all network data private while still delivering real-time monitoring, and rapid threat detection.
The more important part, the heart of the project, which is the machine learning model that kind of does all the magic behind this. I will talk about like how we came up with the solution for this. So first of all, we tried with two very simple models, which were linear regression and logistic regression. And as you can see over here, their accuracy stats were actually very low and definitely unusable. For the case of linear regression over here, it only produces 62% accuracy, so it was very low. And then we kind of went forward with something in hindsight I think was a little bit of an overkill, but we went for the neural network. We used CNN and FNN and a hybrid version of it, and we achieved an accuracy of 81%, which was seemingly pretty good and decent. However, the big problem was that there was actually an overfit. It actually overfit the training data set, and the real accuracy was only about like 74%, which was not really that great. So we think ourselves like, how can we like pull this off? And then we came up with the strategy of dividing the model into two stages to kind of like balance out the workload that each model has to do. So both of the stages actually use random forest because it works very well with tabular dataset, which was the dataset that we were having at the time for training the model. The first stage was actually a binary detection. It's going to determine whether a network flow is actually benign or whether it has any sort of abnormalities. And then if the abnormality is detected, then it will be sent to the second stage, which is going to categorize what threat it could be. For the first stage, we actually achieved an accuracy of 99%, and as you can see over here, the second stage we achieved an accuracy of 86%. And this is a chart of how our system performs on average. Higher probabilities of attacks means lower accuracy, but let's remember that it will never sink below 86% because of the stage 2's accuracy.
So now let's start our demonstration for our application. So this is NetSentinel, our application. This is monitor our network in real time and detect anomalies using AI. And here there are three different pages in our application: the dashboard, the live traffic, and threads. And let's talk about the dashboard page first. So as you can see at the top of the dashboard page, you can see the live metrics, that like the overall risk score, the network health, the security score, performance, and all the active devices. And scrolling down, you can see some of the table that displaying the device monitoring with some statistics, including host name, IP, MAC address, type, operation system, and so more. Scrolling down, you can also see some of the charts that visualize the device type distribution, with the workstation populating the most, and router too. You can also see the operating system distribution, including the bar chart here, and also the donut chart that is displaying the device rigs over here too. And moving on to the live traffic section, you can this is the page where we can also we detect the network packet capture that capture all the packets in the current network. So if someone go here and they can see which IP is like talking to the most, and you can see this the top talkers table, the chart that displaying the most talkative IP. You can see also over here the total connections, the network health, some of the live metrics too. And scrolling down, you can also see the protocol distribution that displaying by a pie chart, a top port that displaying the ports that is connected to the most, and also see the applications where we can see which protocol it is using. So it is like the HTTPS. And when you're scrolling down here, you can also see some of the recent packets that displaying all the recent packets that it is in my current network. And you can also clear and stop capture the network packets anytime you want.
So as you can see here, this is the network threat detection system that we developed for our NetSentinel project. I just clear a log so it doesn't display the threat flows now. But as you can see, it is detecting the benign flows that is happening within the system right now. So if there is a threat, so I can just here use a packet replay applications, and then I will replay a PCAP that contains a thread right now. So in a while, as you can see here, it is returning the threads that I'm replaying within the system right now. Okay, so let me just stop this for a second. And it is displaying the threads that the system can capture within the application. So I want to show something else here, which is when a threat is detected, it will automatically log into two separate files, which are CSV and PCAPs.